All right. Let's see. Let me think. All right, I'm going to show you how to do this both on your calculator and on Desmos. You may use either. I'm inclined to just use Desmos because I think it's a little bit easier, but I'm not sure what you guys will encounter in your college classes. They may expect you to know how to do some of this stuff on your calculator also, so I'm gonna do both out of caution. So you'll need both your computer and your calculator for these. Okay. All right, so I have put on a slide there this basic thing that we have used many times. Just to remind you one more time that you need to know this, because this is key to knowing all of the things you will need to know for your sine and cosine functions. All right. Also, we are going to do all of our sine and cosine applications. We are going to do them in radian mode. Okay, so I'm going to do my answer keys in radians. So everybody right now, put your calculator in radian mode for me. And go ahead. Desmos should probably already be in radian mode because it's the default. But if you hit the wrench right here, you can check it as well. You can do it in degree mode. It's just if some of us are in degree and some of us are in radian, it's going to make our functions completely different and change a lot of things about how we do the problem. So it's just going to be easier if we're all in the same mode. And I will remind you tomorrow to put your calculator in radian mode for the calculator part of it as well. Okay. So far, the stuff that we have done, so we have only used the calculators whenever we were doing triangle trig so far. And everything we did for all of those triangle problems, our angles were all in degrees. We had not done radians yet. So if your angle is in degree, you have to use your calculator in degree mode or it's going to give you the wrong answer. We could do either for this, Caleb. I just want us to all pick one so we're getting the same answers and it's all, standard and consistent. So we could do either one here. And I chose radians because when you get to AP Calculus and do anything like this, everything's always in radians. So I just chose that because we could do either though. Okay. All right. So sine functions can be very helpful for a lot of real life situations. Basically, anything that is periodic or that repeats itself has potential to be modeled by a sine function. Some examples of things that are generally sinusoidal, that's this fancy word right here, sinusoidal, are things like the amount of daylight that we have every day. So, right now we're getting close to December, is it 20th or 21st? 21st, which is our shortest day of the year, right? So we have very little daylight. Then it will get longer till the summer. Then it will get shorter again, and that just continues every year, right? Now, very interesting thing about that is that, if we want to make a sine function for that, our sine function for what we write at Elkin, North Carolina, is going to be different from the sine function that should be written in other parts of the world, right? Most of the time it's not very noticeable. Like if we go from Elkin to, Raleigh or somewhere, there technically would be a little bit of difference, but it would not be noticeable at all. Elkin to Florida, it might be measurable, but it probably still wouldn't even be like enough for you to actually notice as far as your daily life. But if you go up to Alaska, particularly northern Alaska or Canada somewhere, you're going to notice because you might not have but 2 hours of daylight, right? It's going to make a big difference further there, so you're going to definitely need a different function there than you need here. Ocean tides follow a generally sinusoidal function. Now, weather does affect them as well, so if you have we did a project with this one year, and students chose a location that had a hurricane within the last, few days, and their data was all over the place, and we couldn't do anything with their data because obviously, like ocean tides, when you have a hurricane, are going to be like the height of the water in your inlet or whatever is going to be like all over the place with a hurricane. But they follow a generally sinusoidal pattern. Temperatures throughout the year are generally going to be sinusoidal in most areas. Colder in the winter, warmer in the summer, colder again in the winter, and that's going to follow a sinusoidal function. And so there's lots of things that you could apply this to, right? Basically anything that you see happening sort of in a cyclic fashion may apply. That is one thing that they certainly look at because you're always going to have fluctuations, right? So they can look at what the averages would be over long periods of time, and they can compare what, it should be, if you take this period of time, that sine function should do like this or close to this and keep the same versus what it would look like, we would see that possibly going up or down. So it certainly could be used in analyzing what you're seeing there. So I don't think you would necessarily be trying to write the function that is going to, increase that way, but you certainly would compare what you would see as like a steady to maybe what you're seeing in actual patterns today to see if there is a difference. Because, we always have warmer times and colder times, colder winters, warmer winters, things like that. So you're always going to see some fluctuations. We used to have a custodian that would come in, and he would, like on hot days, he would always say that he thought there was something to that global warming, and then on cold days he would say that there was nothing to it, and it used to drive your mom crazy. I thought it was amusing, but she didn't think it was as amusing. But like you have to look at those in like grand scheme of things sort of thing, because you're not going to be able to see that by your personal experiences or by looking at the last 5 years, right? Because you would just see short patterns. That's something very interesting that you would want to look at there. And when you're talking about like things like that, you're talking about fractions of a degrees a lot of times. So the fractions of a degrees, you could, even if you don't account for global warming, you can still make pretty good predictions for short periods of time. It may not be applicable for finding the temperature in July in, 2,300. But July, 10 years from now, it should probably still be relatively applicable there. So let's do this first on the calculator. So what we have here, this was from the textbook, so when it says this page 387, I don't pass out the textbooks anymore. But this was hours of daylight. I can't remember the location that it was looking at. I want to say Chicago, but I might be wrong. But it's a relatively normal place. It's not like Alaska or anything. So let's get our calculators. We're going to do the calculator first. All right, so we are going to first enter our data into L1 and L2. I realize you guys probably have not used the calculator as much as Desmos. How do you get to L1 and L2? Do you guys remember? Stat. So you're going to hit the stat button to get there. Stat, and then edit. So stat button is right here. Edit is number 1, and then you're just going to enter your data. So, okay. So everybody got their data in? Okay. Once you have all of your data entered, you are going to go back to Stat. Then up here at the top you should see Calc. So you're going to go over so that you can select Calc. And then I think it is the very last one. On mine it's the last one, but you guys may have more options than me. C is sine reg. That is your sine regression. And you're going to hit enter and then enter one more time. And it hopefully is going to give us these numbers I have here. If you have the fancier calculators, it is, alright, so if you have the fancier calculator, it gives you another screen in between there. And at the bottom of that, you see calculate. So if you go all the way down and choose calculate, it'll do it. Yeah, that's your answer. That's what I have here. Yeah. Hopefully. So I got 1.598 for my A. I got 0.512 if I round to 3 places for my B. I got negative 1.603 for my C and 12.116 for my D. If you do not have that, then it might be because one of your numbers is typed in incorrectly. That's usually the problem, is you typed in something wrong in your table. Once you do the L1 and L2, you are going to go to Stat. The directions are there at the bottom of this slide here. Stat, over to Calc, and then C sine reg is the one you want to choose, the one at the bottom. Correct.
So if it were to say write the equation,
like the one that we just did,
yes.
It's going to be on the calculator in active section, but yes, theoretically you could do that. What you would have to do though first, Caleb, is you would have to have points to plug in.
That's what I'm saying.
Yeah.
Instead of like saying graphing that
Right.
on a graph, you could just put that table in your calculator.
Yeah, if you had like
and get the same thing instead of looking at the graph and trying to figure out. Okay.
yeah, you'd have to pull points from your graph and make a table from it. But yeah, you could do that. But it will be on calculator inactive, so you can't. But yeah, A, B, C, and D. Yeah. Then we'll do some other like questions with that as well. But the way I've got it on the quiz, the first question will ask you to find a regression. All right, everybody listen, because you're gonna have the same question. Macy asked what this would look like on the quiz. It will have on the quiz. What I'm going to do is the first question on the calculator active section will have some table of data. And it will ask you to find a regression, and then it will ask you for the values of A, B, C, and D, and you will type those in. So that is all it's going to ask you on like number 1 of the calculator active section. What we're about to do is we're about to take this equation and answer other questions about it. So the calculator active section will also have those types of questions that we're getting ready to do. But I will always give you the equation first. The reason is just for my own sanity in grading, because if you mess up the equation, you will miss everything else, even if it's just by like a small decimal point sort of thing. So on the quiz, there will only be one that you have to do this for, and then the rest of them will just give you the equation like it's already been found for you, and ask you other things about it. Okay? All right, I would also like for you to know how to do this on Desmos, so let's look and see how you do this on Desmos. Because Desmos is a lot easier to work with the graph on. So if we pull up Desmos here, you can have either on that section. Yeah, either one on that section. So I will have it embedded where you can use Desmos if you would like on that. So you may use either tomorrow or both, whichever you prefer. Some students sometimes find their equation on the calculator and then graph it in Desmos because the graph is easier. So, yeah, it'll be embedded. All right, so with Desmos, to add your data on Desmos, you just click the plus sign and choose table, and then you're going to add your data there. So try that on your computer. The nice thing about Desmos is just how good of a graph that you get whenever you're, and it automatically pulls up for you. Yes. The plus sign up here in the corner, and then there's an option for table.
Oh, I didn't see.
Yeah. And then, once you have entered your data in the table, in the next line, you're going to type in this equation right here. Y1, and when you type a 1 behind a Y, it's going to make it a subscript, which is what we want. If you look at your table, it doesn't just have X, Y, it has X1, Y1. That's why you have to have that there. You're going to do squiggle, which is shift and the key up there in the corner beside of your 1. So upper left-hand corner beside of your 1. I think it's only a tilde if it's over a letter, but it's like the tilde that is over the N. I don't know its official name.
I mean,
I'm sure it has one.
I'm pretty sure it's a tilde, but it's a math. It makes like,
Yeah. I don't think that we can transfer that here, but we'll look up its official name later. But let's get through. All right, a sine of bx1 plus c plus d. And here is what that should look like. Now, you will notice a couple things here. Actually, did I change it from here? Actually, it's exactly the same this time. Used to, whenever I did these, the Desmos calculator gave just a slightly different answer than the calculator, but it's exactly the same this time. It is because your table right here has a 1 behind the x and the 1 behind that y. And if you don't, it doesn't know that it's pulling values from that table. It thinks you're just trying to graph a regular x and y. You need sign in there probably. I prefer Desmos particularly for the graphing. I find it much easier. But you can use the calculator if you prefer. I mostly wanted to show you the calculator because who knows, you may get a professor in college that does not let you use Desmos. Yes. Yes. I will not tell you these steps. Okay. This is just your equation we've been doing, right?
It's just the y1.
Throw a 1 behind your x and y, put a squiggle there. Yeah. This is the equation we've been using the whole time, right? A sine x, sine bx plus c plus d. So I think this is the easiest because it's all basically the same.
I would still remember the
Yeah. So, all right, questions on finding this? All right, we need to move on. We're running short on time. Okay, so, all right, we're just going to, now that we have this equation, because I don't have this like stored into my calculator, I'm just going to use the 3 decimal places to find these here. So, if I am looking for all of these pieces, then my amplitude is going to be 1.598. Right? My vertical shift is going to be up 12.116, which means my midline is y equals 12.116. So period. Another reason I want you to use radians is because if you're using degrees, you have to change our rules that we've been using. You have to do 360 divided by b instead of 2 pi divided by b. So this makes it where we don't have to change our rules. So 2 pi divided by b, which is 0.512. Since that's a decimal, let's just go ahead and type that in and get the decimal that it equals. 2 pi divided by 0.512, 12.272. And then our phase shift is just going to be 1.603 divided by 0.512. 1.603 divided by 0.512. 3.131. I think that one would be to the right. Yep. Okay, so all of that stuff is the same as everything we've been doing already. It's just we have decimals that we're dealing with, and you'll be allowed to use your calculator to deal with those. Now, what is going to be important, though, is knowing how this applies to the situation. Okay? So, I wanted us to find all of this first so we could see you just find all of these things the same way that you do with the other problems. But the questions that are asked are not going to just say, what's the amplitude of this function? Right? It's going to be in context of what is happening. So, this is more like what the actual questions will look like. We're still looking at the same equation, same situation. So the midline is at 12.116. What does this mean within context of the problem? What does that tell you about our situation? Okay. All right, but I'm not worried. I don't want to hear middle of the graph. I want to hear about our situation, which was dealing with months and hours of daylight. Okay, I like what Maggie has said here. This is the average hours of daylight. Is 12.116 hours. Because if you think of this graph here that we are looking at, on that y-axis you have hours of daylight. And on the x-axis you have months. Yes. I mean, it may, because it's going to be on Canvas, it'll probably be worded like, it may be worded more like what are the average hours of daylight or something like that. Or it might be multiple choice where you have several options, something that this might be an answer choice. It might say something like, this repeats every 12.116 months, like some other distractors. So you won't be typing this in, but it'll either be multiple choice or they'll ask you what is the average hours of daylight. Okay? And if we think about the midline, it is y equals, so it's hours of daylight equals this, right? And it goes through the middle. So that would be our average hours of daylight. Okay, what does that amplitude mean within our context here? What does that tell us?
The days that there was most daylight.
So write it in a sentence that uses 1.598. Write it in a sentence that uses 1.598. Okay, I'm going to write down what Sophie said because she's close. The maximum amount of daylight hours was 1.598. That'd be hours, right? Does that make sense? 1.598 hours of daylight is very little daylight. But we could add a phrase to the end of this that would make it correct. Amplitude is not our maximum value. It's from the midline to the maximum value, right? So the maximum would be 1.598 hours above what? The average. So the maximum amount of daylight was 1.598 hours greater than average. So the only time that your amplitude is your maximum is if your midline is on the axis and has not been moved, right? But in this case, our average, our midline is higher. Does that make sense? All right, what about 12.27? This is our period. When we're looking at the period for the graph, are we looking at the x-axis or the y-axis? X-axis. And we are looking like from here until we see it repeat again. Right? Because period tells us how long it takes something to repeat. What is the something that is repeating here? Okay, so this 12.27 would be months. So can you tell me a sentence that includes that 12.27 for this situation? Okay, so what would use 12.27 in that sentence, Maggie? So how about something like this? The amount of daylight will begin to repeat after 12.27 months. Now, based upon what you know about reality on planet Earth, what should that number be based on what you know about reality? Should be 12 exactly, right? But we have taken data points that are not precise. Perhaps the amount of daylight could have been factored in by weather or something, so it may not be exact. And that is why we see some variation here. Yes? Right, but it would not be a whole 0.27 more. Yeah. Mm-hmm. Yeah, your x-axis is in months. Yeah. Right, because on your x-axis, your x values are months. That's more like a deeper philosophical, like that's more like a deeper scientific question on why it's happening. So that's not exactly what we're looking for. All right, so let's look at this. Okay, here is our graph for. Here's our graph. And actually, I don't even have to write on this. Let me do this instead. All right, let's do this. Let's pretend, I'm going to type this in, 1.598 sine of 0.512 x minus 1.6, I'm sorry, plus 12.116. So I type this in without the C, which means it would be this graph without a phase shift. What's the issue? Why does it need that phase shift? So if we don't, so right here, really, if we wanted to, a cosine function would not have to have been shifted as much, right? Because we're pretty close to a